All right, here's the lecture for Chapter 2, Section 9, Stress Transformation Equations for Plane Stress. Jump into it. Our course learning objectives. So from the course learning objective sheet, we're attacking number 2 still. This is actually the middle of 3 that are going after this objective of being able to convert or do transformation so that we can look at the stresses at a point. We can look at them in any orientation. We're not bound by the way that they're handed to us. And that's important because we want to be masters of our own coordinate system. We want to be able to do the problem in the way that it makes sense and then convert the answer to the way that we need to understand it. So that's what this is all about. The equations that we're going to use are the equations that come out in this section now are the next set of equations on the study guide, the equations 212 and 213, where we are doing the stress transformations. And so we'll touch more on those as we go through them, so I won't cover it now. So in the last video, or in section 2.6, chapter 2, section 6, we did a simple transformation where we had taken this tensile member and we had cut it on a different plane, so it was no longer normal to that stress, and we wanted to figure out the normal and the shear stresses that were going on that cut plane. And we derived these two equations shown on the side. And so now we're going one step farther. We don't want to deal with just a simple pulling it in one direction. We want something much more difficult. We're going to pull it in all directions. We're going to pull it up. We're going to pull it left and right. We're going to pull it, well, if we pull it up, there has to be a reaction force pulling it down because it's static. It's not accelerating. And then we're going to have shear forces on this as well. So my shear forces in those directions. All right. And so we're going to look at this on an arbitrary plane. That arbitrary plane looks like, there you go. There's our arbitrary plane. And if I get rid of all the junk that I've just added onto this, they're defining this angle theta this way. Now we defined it using using our coordinate system last time like that. But if we look at this, here's our situation. Here's our stress in the x direction. We know we have that equal and opposite, so I also have stress in that direction, in the other, or in the positive x direction. And now my coordinate system, I'm going to draw it in red because I'm trying to stay in that habit. Try to use that when I go to paper too. I've got my x and my y. Now my normal coordinate, my normal vector is this way. And that puts this as theta. And so this picture, that picture with that definition of theta matches, it does match. Those two go together. This stress cube and this stress system there match up with each other. So that's important. That's important. How do we do this transformation? Well, the way that we're going to do that, we're going to go back to this picture, which is just this little stress, just that little section, and we're going to execute a force balance. We are going to, the way that this has been done is we're going to do a sum of the forces in the n direction are equal to 0. Now, the reason I'm doing the sum of the forces in the n direction is the stresses in the nt, the shear stresses, don't show up. They're perpendicular to the n direction, so they don't show up. So I'm going to get an equation which is then a function of the stresses in the n direction and everything else except for that. So we'll walk through this, just take a couple minutes. We'll walk through that, show how what happens And then if you wanted to do that for the shear direction, I'll leave that up to you. But the first term that's going to show up, get the right color, the first term that's going to show up in my equation, the first force is from this normal stress in the n direction. So that is sigma n times that element of area, this element of area, that whole face. And that is dA. The second, that term's complete. We can check that little box. The second term that we've got, we'll go here to sigma x. Now sigma x is in the opposite direction of, remember this is my n direction. So sigma x is in the opposite direction. I'm going to put it right here, minus sigma x. Now that's the stress. To turn that into a force, I have to multiply that by the area that it works across. And this area is the same as that element of area, but it's smaller by the term cosine theta. All right, so this is sigma x dA cosine theta. Now, that's the force. How much of that is in the n direction? Well, I get one more cosine theta. If I would think about this force going in this direction, that's my x, and here's theta again. That component in that direction, I have to add. That's the ratio of it that's going in that direction. So I've got two cosine terms, one that's reducing the area and one that's reducing the force. All right. Put my little check mark. I got that one done. I'm going to jump down now to do that term. And that's going to look like it's in the opposite direction as n, or it's opposed. It's not opposite, but it's opposed. It's generally opposed. And that's going to give me sigma y. And then I've got my area term. Now it's no longer dA cosine, it's dA sine theta. And that's, again, that's my force. Now I need to take into account that it's not in the same direction. Well, how much of it do I use? Well, now it's the sine theta. All right. And then I've got a term that I skipped. Then we've got two terms that we skipped. And you know what? I'm going to pause this and I'm going to get rid of my picture. Oh, and then never mind. I can't get rid of my picture. We'll just start writing over here. I got two other terms. I've got this term which is acting downward, okay, but that's opposed to the direction of n. So it's a minus the shear in the xy direction. It's acting on this face which is dA cosine theta. Now, how much of it is acting in that direction? Well, in the same way that with this term we use sine for the direction, that's acting in the same direction that that is. So I'm going to add a sine term there. So here's my force, and this is for the direction. I've got one more term. I've got this shear term. That also is acting generally opposed. It's minus tau xy. It's on the dA sine theta face. But now it's acting in the same way as that, so it's cosine theta. All right? Now we can start combining all those things together. All right? Let's go to the next slide. It looks like if I write this out one more time, it's going to be 0 is equal to, oh, sorry, got it wrong already. 0 is equal to sigma n dA minus sigma x dA cosine squared theta minus, got it wrong again, got a sigma y dA sine squared theta minus, okay, here's a trick. Tau xy is the same as tau yx. That shear stress has to be the same because otherwise it would cause our stress square to spin. Little side note here, let's draw it. I've got that going up and that going down. Those are opposite, and this and that. And there's only one value there. It's tau xy. And we'll spend a little more time on that shortly. But those all have to be the same, or this would spin or rotate, but it doesn't. So we've got one value. So instead of saying minus tau xy and then having a term, I'm going to condense those two terms together. So I've got 2 tau xy times the dA, and then it was a cosine theta sine theta. Now, the next thing I'm going to do, I want to solve this in terms of sigma n. So I've got sigma n is equal to, and all of those terms become positive, sigma x cosine squared theta plus sigma y sine squared theta plus 2 tau xy cosine theta sine theta. Made it fit. Got it. And that's our equation, so that if we know, if we start out with this stress cube in any orientation, I've got a stress in the y direction there, I've got a stress in the x direction there, I'm going to have their equal and opposite, and then on top of that I'm also going to add my shear forces, tau xy. I can take that, and for any arbitrary angle, one more color, for any arbitrary cut that we put, I can determine what the normal stress is going to be with this equation. Now, the same as we did in section 6, we're going to use some fancy trick, and we're going to come up with we're going to change this equation to get rid of cosine squared and sine squared and a cosine sine. And is it important? Is it valuable? It depends on how you solve the problem. It depends on the problem you approach. Sometimes it's easier to use this formulation, and sometimes the other one. So here are what those equations look like from the study guide. This is the one, that's the formula that we just derived. And then, as the book says, in terms of the double angle, here's this new formulation that we get sigma x plus sigma y over 2 plus the difference over 2 times cosine 2 theta. Yeah, really, that's better? It actually, it can be, and that's going to be coming up in 2 more sections when we go and look at this a different way. And it will, it can help. It can help you visualize this stuff. If you went through and derived the shear stress transformation, if we did a sum of the forces in the shear in the t direction, then we would get that shear in the nt direction. And that equation, as we derive it, it would come out like this. And then you get this double angle formulation that looks like that. And I know for the homework that we're going to hit in this section, stick with the blue circles. Don't mess with the other ones. Long term, you'll have to make your own choice. I probably, believe it or not, I mess with these a lot in what I do, but that requires the tricks that we're going to learn later in the chapter, and you really have to start loving those tricks. And that may be a stretch. You guys may not love them the way I do, and I get that. And that's okay. That's okay. One thing we got to talk about before we leave this topic and that is sign convention. I've talked about this in some of the homework that I've done. Tension is positive, and so when we draw our stress cube, we drew our system like this, and those were all positive stresses, and we derived things that way, and so we've got to be consistent. That is a force in that direction pushing away, and so tension is a positive force. We've got to embrace that. We could have derived the equations a different way, but we didn't, and so we want to stick with, we need to, in order to be consistent, we need to have that going. Shear stress is more challenging to define. Shear stress is more challenging to define. And here's the trick I'm going to work with you on is, if we imagine a coordinate system at the center of that cube, then this helps. If I am looking at what I'm going to call now my turquoise, my blue face, all right? Actually, let's call a blue face and a green face, and we'll get them both out there. Now, one of those is a face that I'm going to say is, trying to get the right color, it is the positive X face. In other words, since my coordinate system is at the center, and I know this stress cube is infinitesimal, but my origin is at the center of that infinitesimal. One of those faces is on the plus face, and one of those is on the minus X face. So this blue face is, and it makes sense, that's on the positive side of the axis. This green is going to be the minus X face. All right? If I have a shear stress, oh, I don't want to use red. I don't want to use red. I'm going to purple. If I have a shear stress that's going to be like this, we know those are all going to be the same. This shear stress is on the positive face, and it points in the positive Y. This, on the green face, this is going to be a negative, that's the negative face, negative X, and it's pointing in the negative Y. In both cases, positive X, positive Y, that's going to be a positive shear in the XY. This is a negative X in the negative Y, and that's also going to be a positive tau XY. Because I've got two negatives, that makes a positive. Now let's look at this face. Let's look at it in the Y direction a sec. Oh, let's pick two more colors. We're going to go with this orange. We don't need to do both, actually. We'll just do one of them. I think we can do one. That is going to be the positive Y face, right? And that's going to be pointing in the positive X direction. So it also is a positive tau XY. And so you can figure out how this bottom one works. And we'll go to black because white would really be bad. That black face, that's the negative Y face. And we're pointing in the negative Y, or sorry, the negative X direction. Two negatives, that's also a positive. It's a little more challenge we have to think about. We've got one more thing. We've actually got two things to think about, which face and which direction. But that helps us define that. So that system of shear is going to be positive. That's going to result in this stress cube stretching like that. Does that make sense? Yeah, probably not. Let's exaggerate a little bit more. It's going to take this stress cube and it's going to take it like this. That's how it's going to deflect. That's a positive shear. If I had negative shear, well, I almost wish I had one more slide. We could talk about that. Negative shear is going to be in the other direction. So a negative shear stress is going to look like this. And that's a negative tau xy. All right. Next sign convention. The angle, well, this is what we've been talking about. The angle is positive counterclockwise from x. So when I draw my coordinate system, x, y, and I put my new system on top of that, n and t, that's theta. Positive counterclockwise from x to y. And when I say that follows the right-hand rule, that's because angles would be measured from x to y, right? All right. Last one, n, t, and z. We have this. I'll redraw it. We've got n and t. Z is going to be coming out of the page at us. That's my z direction. And the z would be the same as the z for this xy coordinate system, right? I put x and y. Z is going to be that same one. Z is in that same direction. All right. Next presentation, we will do a stress transformation working through example problem 2.8. See you then.